So much for having me. Great. That's should I?
Yeah, totally.
Well, it just occurred to me that she's giving it dual pod, so how does that get recorded?
The video should be on YouTube also, and Isabel is managing the camera.
Okay.
Is there a reason why it's not lowered completely?
Yes.
Yes. So I'm gonna do it on the chalkboard. So we're gonna go up and down. So hello, I'm your most troublesome speaker of the semester so far. Thanks for having me, so I can rabble rouse here, I guess.
We like chalk.
Yeah, that was fun. Yeah, so I'm Cari. I'm going to be talking about a paper I wrote a couple months ago in response to this measurement of the W mass measured by CDF-II. So what I really appreciate about NYU is that there's so many different theory interests in this one group. So I tried to write a talk that isn't exclusively for collider physicists. So if I say anything confusing, please stop me. And hopefully this kind of gives you some idea about what the anomaly is, whether to believe it, and how it might be resolved. Perfect. Okay. Good. All right. So the outline of my talk. First, I want to go over a bit of the history of the W mass, why it's hard to measure, and how we've measured it so far. Then I'll talk about how we address this anomalous mass using what we call the electroweak precision fit, and we can parameterize the physics effects there. Then I'll go into some models that we consider about how to resolve this, and then ultimately end with a discussion about what this kind of anomaly would mean for the future of particle physics. So again, feel free to stop me at any point, or feel free to ask for clarification. So getting started with the history. All right, so certainly all of us know that the W mass is a gauge boson of the electroweak theory in the standard model. So we have our Lagrangian. It includes, let me know if this is annoying. I can't do anything about it, just let me know, I guess. All right, where we have this SU2 left cross U1 hypercharge, which we know now spontaneously breaks down to a U1 EMF. Okay, so the W mass was a really important part of this story because first finding the Higgs and then measuring the W mass to be consistent with this picture of spontaneous symmetry breaking was an excellent confirmation of our expectations of the standard model. So really having our Higgs, which we found in this representation under the gauge groups, and then the thank you. Okay. What's going on? Okay. And then these degrees of freedom reorganizing into the Higgs that we know and love, the W masses and the Z boson. All this picture was really important for understanding what the pattern of spontaneous symmetry breaking was. So knowing that it is something that's so essential for confirming this theory that we're all taught to believe, why is it so hard to measure? Well, usually what we like to think of when we think of measuring a mass is we like to think of a resonance, right? There's some resonance in terms of the 4 momentum squared is going to give us some mass bump that we should be able to see clearly in some experimental spectrum. So if you want to compare this very clear canonical story for something like the Z boson is neutral, so we know it can go to plus and minus lepton pairs. So whenever we do this, we can see very clearly, if we look at some spectrum of the invariant mass of something like a 2 muon system, we'll see something that looks very clearly like this, sitting right at the mass of the Z. So this is very straightforward because leptons are clean, and we can just kind of pull this out of experimental data. So doing measurements like this are a little bit more straightforward. Okay, for W's, we don't have that same story. So let's consider a W plus, obviously same story for W minus, just flip all the charges. These things don't decay into plus and minus lepton pairs, but they decay into either leptons and their neutrinos of the same flavor, or they go into hadrons. They can tie up-type and down-type quarks together. So these things are much harder to look for experimentally. One of them is obvious because if we have a neutrino in our final state, we have some missing energy signature. So the same picture that we have here, where we can just reconstruct the four momenta and calculate invariant mass, isn't going to work, because now there's missing energy that makes it impossible to do that calculation. Okay, for the hadrons, it's still hard too, because everything will hadronize, and we have jets. And jets are these big, messy, kind of mysterious objects that certainly won't give us the same kind of precision as this very clean single lepton signature would. So these kind of conspire to make the W a much more complicated mass measurement, which is why it's something that has kind of been a more interesting work in progress over the last decades even. So given that this is our story, how do we actually get a clean experimental mass measurement? And the way that we do that is not by looking at something like this, where we have an invariant signal like this. What we instead look for is kinematics. So what usually they do in experiments is they do consider this channel where they have that very clean lepton, but there's the missing energy. And what they want to do is they want to look at, again, the signal that has kind of the least background or noise going with it. And that's going to be the transverse momentum of our lepton. So what they do, I think this is if we look at a distribution in the PT of your lepton, all right, and here's our frequency, what we'll see is there's this very clear kinematic peak that shows up right at the mass of the W divided by 2. Right? So obviously it's not going to be a delta function like that beautiful signature over there, because things get smeared out, there's two things recoiling against each other, but we understand that this should be the peak in the distribution. So they do some fits, they find out, okay, this is going to be at about 40 GeV, and by fitting this experimental data, we're able to extract what the mass of the W should be. So it is a very different looking kind of experimental thing. But in order to do this, you need a lot more theoretical input to figure out what the W mass actually is in this calculation. So other things that are important to calculating this kinematic distribution are going to be things like the width of the W, and the parton distribution functions of the quarks coming in. So if we're producing a W like this, understand what momentum we'll see in our W, we need to understand what momentum is going in here too. So there's a lot of kind of tricky experimental things or other theoretical objects that need to enter this calculation. So while it is kind of a simpler fitting procedure, it's still very difficult and depends a lot about the structure of the standard model and what we assume goes into the model for the W mass. Okay. Moreover, these PDFs, the distribution of momentum of the quarks, are objects that have a high theoretical uncertainty. And they're things that are being studied ongoing. So definitely as we improve things like this, as we improve other measurements, we expect that the W mass should improve. So while it's not surprising that new measurements are coming out of the W, this is not something that we've completely nailed down. Exactly what goes into the calculation, a lot of these things are still ongoing calculations as well. Okay, so that being said, let's go into a little bit the current state of affairs with our W mass measurements. Okay, so here is the summary of the different measurements that have happened so far for the W mass. So first, just to draw your attention, this line right here is the theoretical prediction of the standard model. Sorry.
One on the right. One on the right.
Okay. Thank you. Yeah, I can try to handle more slides later on. But all right, so our standard model prediction is this line here. All right, and then before we look at the CDF-II measurements, we can look at the things that have shown up beforehand. So we see, even before we consider the CDF-II result, a lot of these experimental measurements have been already pulling high on the W mass. Okay, but certainly none of them are claiming to pull that high with that little of an error bar before. So before we had the CDF-II measurement, the PDG world average was reporting this number up here, this 80.38 GeV max, which is still, you know, a little bit higher with expectation of what the standard model would give. If we just consider the CDF-II result, that's this amazing 80.43 number with extremely tiny error bars. So if you've heard in the news anything about like, this is a 7 sigma anomaly, this is the number they're quoting if this is your sigma, okay? So, but just saying alone that it's measured something that's 7 sigma anomalous with the standard model is a little bit too uncharitable, I guess, if you want to say it like that. Because a world average of these things would very clearly bring down that central value quite a bit. But still, it is interesting to note that there is a lot of pull towards a higher mass than we would expect.
Is there any particular reason why like CMS haven't done this measurement?
CMS is working on this measurement. Yeah, great question. I think, and if anyone who knows better about CMS, is this a CMS or
I
IMS tool?
actually, no, it's not a CMS. I happen to have discussed it with the CMS.
Yeah, please.
The person who was the spokesperson in this epic, when they could have done it. And he said that there was a big mentality within the collaboration not to publish something where they weren't getting a better answer than everybody else. And when you do the errors carefully on this and include the transverse momentum uncertainties and so on, they would have actually shown that you can't get such a great fit.
Wow.
And so there was internal opposition,
I see.
and which he couldn't overcome. But obviously now with the CDF one there.
So they're also seeing an anomalously high.
No,
they're
I
not.
misunderstood. They would have concluded had they done the analysis, because they could have done it years ago.
Mhm.
They could have reported it. They would have concluded that it had an intrinsically big error.
Oh, I
Because
see,
there's
I
a
see.
lot of uncertainty,
Absolutely.
especially in the PT distribution of PDFs.
Yeah.
And there was a mentality, he said, within CMS, that unless they had a smaller error,
Yeah.
they wouldn't publish, even though, of course, from an outside standpoint, publishing with a larger error when there's a really good reason and you're showing that the error is intrinsically larger would have been a contribution. Anyway, that's
Okay.
private information, one might say, but it's entertaining.
Private information just recorded to upload to YouTube.
For curiosity, is there a similar plot for Z-mass? I mean, of course, we can measure Z-mass much better, but let's say we forget that and apply the same methods to Z-boson. Is there similar, just to compare it for?
You mean like is
Just basically,
is there like a summary from all the different experiments?
no, I mean by
CMS?
using similar methods,
Oh, by
like you
using
look
kinematics.
right.
I don't know if anyone's done the analysis like that.
I think it's actually in the, people do that.
People do that?
What do
And
you
there's
mean?
some reason that it's, I guess they mostly look at the muons, don't they?
Yeah, so
And-
usually they look at either the E plus E minus or dimuon final state.
Right, and
Right,
there's
but that
some
would be-
reason that.
Because systematics is probably similar, right? That would be a nice cross-check of the
Wow.
systematic for W.
What you really would want is for them to go back, and this I know they haven't done, and like take your data and then just say like, I'm going to forget I ever saw one of these leptons.
Sure.
Right, that's
Maybe
what
That's what
I
he's
meant.
talking
Yeah,
Yeah,
they have not done that.
I remember there was a discussion in the period where CDF was reporting it, and I can't remember though, but there was some claim that that's not as easy, it's not as obvious as one might think, but I don't remember the argument, I'm sorry.
So, I mean, well, trust experimentalists are doing a good job with the data sets and the validation. So I just want to comment on some things as to why the split from CDF-II might be, you know, at least why it's different from the Atlas measurement that was published very recently and the CMS one that is to come out. So for starters, the CDF-II was done at the Tevatron. So the Tevatron is run, it's a different kind of experiment than the LHC. So it's run at a center of mass energy of 1.96 TeV. So definitely a different energy scale that we're working on that can affect detectors, uncertainties, things like that. And it's not a proton-proton collider, it's a proton-antiproton collider. So like we're saying, the PDFs of these quarks can really affect a lot these error bars. And the PDFs for a proton versus an antiproton will give you a different story, right? So there are some things that are inherently different about the experimental setup, so it's not necessarily going to be an apples-to-apples comparison for these things.
It's a D0 it is, so
Yeah.
why is D0 such a bigger error?
Yeah, so let me say some of the things that have improved over the past decades since they collected this data as to why the error bars might shrink.
Did you mention Atlas being recent? I missed when you said it was actually. This last Atlas number, did you say it's just recently come out? When was that? I just didn't hear you.
I'm saying it quietly because I'm not confident, but I think like 2016 or something like that.
Oh, so it's not now.
No, no,
I'm
no,
sorry,
no,
I thought
no,
you were saying
no,
it's now. Okay.
No.
Is
But-
this list the chronological?
Yes.
List of data?
Yeah, and what's interesting too is if you look at the CDF-I, it has almost the exact same central value as CDF-II, which I mean, okay. So some things that have improved since the last CDF measurement and all of these other experiments earlier on is again, QCD progress in PDF understanding, so that's improved that kind of uncertainty. Things that are interesting that happened 11 years after the data set was collected, because this data set was published and finished in 2011. Is they're claiming that they have much better resolution on their PT spectrum of their leptons. So why that's something that came out 10 years after the fact, I'm not quite sure. The PDFs make sense, the tracking maybe not. And something else that they've improved is that they have a factor of 4 times more luminosity. So that should reduce uncertainty for that by a factor of 2, but clearly these error bars are more than a factor of 2.
Is it more Lumi than the D0?
I think so. 4 times more than their first data set, but not 4 times more than D0.
What they said was that they had calibrated their detector very much more accurately by
Yes.
using cosmic rays, where you can see how the particles, and you could actually, in effect, correct for inhomogeneities in the magnetic field and so on.
Mhm.
So I think they did have a legitimate reason
Sure,
of why it would be more accurate, and they had
absolutely.
empirical evidence that it
Yes.
was more accurate by looking at cosmic rays and so on. So
Yeah, so definitely I'm not doubting that their resolution improved between the first and second run. It's just a little interesting that it's like being reported on for the first time.
well, it took them 5 years. It's a hard project.
Oh.
I mean, it's fine as a theoristic, make innuendos on that, but it doesn't seem very appropriate.
Sure, fair enough. These things definitely take time. So, okay. So all these are said, definitely some concrete improvements were made in the CDF measurements. But again, if you take all of these things and you assume that the error bars are uncorrelated and you make an updated world average, the anomaly is much more like a 3 sigma kind of anomaly. So not in your face as 7, but
PDG average versus the CDF-II result is also like 3 sigma difference. Or how? Like if I take the average of everything that's not CDF and I
Yeah.
compare it to CDF, how bad is the tension?
that's a good question. I mean, I guess I could just look at this right now. Yeah, about 3-ish sigma difference, 3 to 4 sigma between the PDF and or PDG and the CDF measurement.
But I don't know if that's really the way that you want to ask. I mean, that's close to the way you want to ask the question, but what you really want to ask is like, if I have all these measurements, is this set of measurements consistent with all coming out of a single value? Which is close to asking the comparison between an average of these things and that,
I agree,
but it's not quite the same question.
I agree. Really,
It's probably not as bad as that.
That's fair.
There's, I've read, and we've heard talks about it, that the standard model prediction is sensitive to alpha, the electric
Yes, absolutely.
alpha at MZ.
Yes.
And with these recent hadronic vacuum polarization changes that are suggested by lattice gauge theory, that affects the running of alpha. Do you know how the sign of that effect affects the standard model prediction here?
I will show you how that works because that will go into part of what we do with the electroweak decision. Yeah, absolutely. Okay,
One on the right. The one on the right.
it's fine.
And press the button. There you go.
Great, okay.
I have a question. So
Yeah.
it sounds like that this improvement in resolution has come from calibrating using cosmic rays. So I was just curious, if they have any other analyses that they similarly rely on sort of having good PT resolution that might see a similar sort of displacement from what has previously been found, or
That is a good question. Again, anyone in the audience, feel free to correct me if I'm wrong, but I think that the W mass is the only measurement that would have improved beyond bounds that could be set by other experiments since then, like Lab or the LHC. So I don't think that there's anything else that would have seen a big improvement from this upgrade in analysis. So that's what the state of the anomaly is. Now I want to talk about what Glennis has alluded to, and that is how this fits into the standard model, which we will parameterize using the electroweak precision thing. Okay. So the idea is that there are other parameters in our theory, the standard model theory, that are measured very well. So even though there are things that have a less precise prediction, we can sort of leverage these things in the very precise prediction to make precise predictions of these other observables. So you kind of have this feed off between known observables and things that you want to understand better. So in our standard model, we have 7 degrees of freedom. So we have 7 free parameters with which you can define the other parameters of the standard model. So we'll take a basis of 7 very well measured observables and then calculate things with this basis. So in our fit, these will be the floats, or observables with which we calculate everything else with. So the things that we use, things that are very well measured. For starters, we have alpha E&M, and in particular, it's measured very well at the electron mass pole. So this is a number that we all know and love so well. And then it's got a bunch of decimal places, whatever, afterwards. And this is measured so extremely well, we just fix this value. We don't even need to float it, the experimental errors are so small. Okay. Something else that's similarly very well measured that we just fix it is G Fermi. So that is the 4 fermion interaction. So if you have a lepton, something like, we've all done this calculation in QFT. If you have the theory of a 4 Fermi interaction, you can parameterize that with G Fermi, and that is also extremely well measured. Okay. So these 2 things we just pin down. Other things that are measured extremely well that we will float, so these are fixed, and the actual floats will be the mass of the Z, as I've said. We've done a very good job measuring it. The mass of the top is actually very well measured too. The mass of the Higgs, alpha is strong at the Z pole. And finally, we have the hadronic contribution. Just alpha, yeah. Again at the Z pole. Okay. So with these 7 parameters, we can calculate any other parameter that we would predict from the standard model. So that's what we'll do. We'll take these things, which have a very narrow error bar, and then use them to predict other observables with also a small error bar using a chi-squared fit. Does that make sense? Any questions so far?
On top is like a few percent, 1 to 2%.
Yeah, I think it's like 0.1 GeVu or so. So
really?
It's a little bit less, like 0.5% even. Okay. So these are the things we know very well. And we want to use this to calculate things that we don't necessarily know as well. So things that usually fit into, we'll say these other observables that are a function of the 7 parameters. Okay. These things usually include, of course, the mass of the W, the width of the W, the width of the Z, a lot of other things. So we have like a hadronic cross-section, asymmetries, stuff like that. All these kinds of things that are also standard model and can be calculated with these parameters. So going to Glennis's point about how do the measurements of these things affect the W mass, we can write down the W mass is a function of these things. And for standard model physics, well, we can calculate it as the following dependence. So I tried to invert this, it's not cute, this is the best way, I'm sorry. Okay. Times, okay, this is equal to n plus These are radiative corrections up to order alpha strong cubed. Okay. So we have a very concise theory of the W mass that can be calculated from just these variables. All right. So we can write down similar kind of functions for all of these other parameters for these guys, and then what we're going to do is a global chi-squared fit. So what we'll be doing is we'll be calculating the chi-squared for the sum over all of the observables that we're interested in, where we take the measured value. Yeah, let me just write it all down. Okay, so here we have MJ is going to be measured from an experiment. OJ is theory as a function of the 7 parameters. And then sigma j is the experimental uncertainty. Okay, and we have this chi-squared fit. And we're going to float our 7 parameters such that we can minimize this chi-squared.
MJ is the location of the peak in the curve that you were drawing just now.
Sorry, J is just like an
MJ,
index.
sorry.
What is it?
MJ is the location of the peak in the
Yeah,
curve that
that's
you were
right. It'll be the central value or something. Yeah.
Does the theory uncertainty and characterize experimental?
Yeah, so there are kind of different ways that people have formulated this. Sometimes they consider this is going to be like an average of the theory or including the theory and experimental uncertainty. For what we do in this paper is we just consider the experimental uncertainty. But you can argue that there are better or worse ways to do the fit by how you include these 2 things. Yeah. Okay. So this is what we are trying to minimize.
Are you going to talk more about that side of the board, like the thing you call delta R?
No, I'm just going to say those are radiative corrections.
Well, I wanted to ask about that and how it's not entirely obvious to me that's entirely short distance, for example. And if there's a long distance component, but I can't do it in my head.
Yeah.
I just thought maybe you could expound on it a little bit.
Sure. I mean, I think, yeah, so these are calculated up to like 2 or 3 loop in terms of QCD corrections.
Right, but could you just draw some of the diagrams? Because, right, if there's a long distance piece, it could have all sorts of uncertainties.
Yeah, I mean, this is really.
So that's sort of not in your domain.
Yeah, this isn't exactly. So I will be talking about how we can correct this with new physics, but with standard model, I think a lattice person would have much smarter things to say about it than I would.
So that's a lattice calculation.
Yeah.
So it must be that it's long distance, otherwise people would do it for turbulence.
So you mentioned that we have MZ measurement pretty accurate. Why do you choose it as a free parameter to discuss?
Yeah, so the idea is that because the central value of this is very well known and the error bars are small, you only have to kind of wiggle it a small amount to see how this would change. So if there were big uncertainties here, then your chi-squared could vary quite a lot. So you want things that are already precise so that your comparison is going to be precise in your chi-squared fit too, if that makes sense. So because it's precise, it's a good thing to float because there's not a wide range of values that it could have, if that makes sense.
I'm sorry, I'm slow to absorb things. The one thing you called, it looked like sigma sub had.
Yeah.
What did you say
This is like the total hadronic scattering cross-section or something that we've measured at the LHC.
What hadronic cross-section?
Inclusive. This inclusive hadronic.
Inclusive for what?
Like we collide protons to get hadronic stuff out at the end.
The total cross-section?
Yeah. Yeah,
Why
again,
does that enter?
So if this doesn't enter the W mass, this is just another observable that we would use for our chi-squared fit. So this would again like be part of the global fit, not necessarily.
Right, but it's absolutely.
Fixes alpha strong.
Oh, probably it's the cross-section for producing Z's or some, or W. Right, because we can't possibly calculate accurately the total hadronic cross-section.
Sure.
But that might fix alpha strong, for example, right? That's one of the.
No. The total cross-section is forward, and so that's got all sorts of long distance. But maybe it's some sort of like, who knows, but we can try to find out.
So yeah, so I mean really what we do with all these other things is we just grab what's going on in the PDG and we put them into our fit. So the things that we really, explore. So we consider how all of these different things have been worked out to include our new physics contributions radiatively. But yeah, I won't say too much about how those things themselves are calculated.
How do you get that formula?
How do you do this formula?
How do you get it?
If you start with the Springer model.
Okay.
Yeah, so I mean, it's really just taking, like, if you throw out this part, it's just tree level standard model.
I see. Yeah.
Yeah, and then you can kind of work backwards, assuming that the fundamental parameters are this and these.
Yeah, I mean, the first thing minus the brackets, this is a tree level.
Yeah, you could work out G Fermi in terms of like the mass of the Z and then like mixing angles and things like that. All of these are related because there's only the 7 degrees of freedom. Cool. So then just to say some things about if we do this fit with the PDG from 2019 result. So before CDF, we have the standard model predictions of things would give us a p-value of 0.45. So we're not so alarmed here. But if we instead use our measured value being the CDF-II result, and again, just the CDF-II result, not the average, then we find that our p-value is 2 times 10 to the minus 7. So just taking that result, again, very shocking, very new, blah, 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 but you gotta take the world average, so. Okay, cool.
Are you gonna say what it is with the average?
With the average, it's again closer to like 2 times 10 to the minus 5 or something. Closer to that 3 sigmas, right? Yeah, it's in our paper, I didn't write it down here, but yeah. Okay, good. So given that there is something kind of anomalous happening, if you include this result, maybe new physics could be an answer. So how can we figure out what new physics would do to this model of prediction? And so what we want to use is this framework called the Oblique Parameters. So the Oblique Parameters, maybe you've heard them as the Peskin-Takeuchi parameters. What these do is they parameterize how new physics interactions can affect the self-energies of gauge bosons and therefore change their mass. So there's a lot of words that mean these same things. So maybe you've heard it as the Fourier transform with the 2-point function, the self-energy, the vacuum polarization, all of these things are kind of the same story, why we call them so many different things. Seems like an exercise to confuse grad students sometimes. But okay, so let's say that we have a propagator. And on one side, we have a vector v, and on the other side, a vector v prime, right? And maybe there's something that'll be contributing some correction to this kind of propagator. Okay, so what we're going to study is this object where we have Fourier transform with a 2-point function as a function of momentum, and then we're just going to do a Taylor expansion in powers of momentum. And I guess, we're concerned up to the second derivatives in this case, but basically this is what we're going to be doing. So you can think about this in a Lagrangian as a term including like, if we have our 2 particles v and v prime, it's going to look like this. So we would expect that at first order, this should just be the mass that we would want, or that we would measure with our standard model theory. Okay, then everything on it is these radiative corrections or momentum dependent new physics. Okay, and there's been kind of a lot of literature that's developed around this, and sometimes some of the literature is not quite as careful. So whenever you're doing something like this, it's extremely careful. You have to be extremely careful to nail down exactly what you mean by your fields. So something that we figured out the hard way writing this paper is that oblique parameters are not necessarily basis independent. You have to work in what's called a universal theory in order for it to be basis independent. So it has a very well-defined way of what particles you can integrate out using equations of motion, how you normalize your fields, and things like that. So a lot of confusion in this literature, if it seems like some things are inconsistent, comes from inconsistent field definitions. So that's just a caveat in case you've seen something that doesn't look like it matches what I'm saying, is there might be a field redefinition behind the scenes. Okay. So if you want to learn more about that, there's this great paper by Kevin Zhang and James Wells, which you should absolutely check out. Okay, not sponsored. Okay. So
Why is momentum the right expansion parameter? I would think it would be operator dimension.
good question. I think it has something to do with word identities that make the momentum the right thing to expand in.
But you're only going to go to p squared? Because I think there are p to the fourth terms that
Yeah.
get
So we'll
treated.
go to, for the radiative corrections, we'll go up to the p to the fourth terms. Okay, so that's oblique parameters in general. What we'll be considering is a set of 3, but secretly just 2 oblique parameters called the ST and U parameters. So extremely frustratingly, these have absolutely nothing to do with the other ST and U parameters that we have all grown to know and love from our UFT classes. So I apologize. So capital ST and U, very different. Okay. And these are not a complete set of operators or of things that will map onto effective operators. There's really 4 more. And choosing these is kind of dependent on what new physics you're assuming to have. So these will map onto certain EFT operators, which will be consistent with the new physics that we're considering. If you do different new physics models, you have to do different electroweak precision stuff there too. So again, just another caveat. Okay. So what these things are is they are again functions of this expansion of our 2-point function over here. So we'll define t first. Okay. W squared minus the 2 points of the z over mt squared. All right, and then x is a little messier. So this is the sine and cosine of the mixing angle, the Weinberg mixing angle. So just the electroweak angle. For alpha, this one's going to be a function of the first derivative of these propagators. This is the only long equation I have, I promise. Okay. And then I won't even bother writing down the u because it's much uglier and we don't even use it in the end. So I'll explain why later, but these are the 2 that are really interesting. And the standard model predicts these to be 0. I think it's easiest to see adjusted t. So again, this is the 2-point function, and when it's at 0 momentum, we expect it to just be the mass of the object. So this should just be, this is the propagator 2-point between a WW, and this is between a Z and a Z. So it's just the mass. Mass of W squared divided by mass of W squared minus mass of Z squared over mass of Z squared, 1 minus 1, 0. So these things in the standard model should be 0. So measuring them to be non-zero would mean that there could be new physics causing some modifications through corrections like this. Okay.
And so the denominators there are the parameters that you extract from alpha and G Fermi, but the numerator is actual pole.
Yeah, I think that's a good way of thinking about it. Yeah. Yeah. So this is like the actual pole from the Fourier transform done in that expansion. Yeah. Okay. So this isn't a super intuitive way to visualize these things. So instead, we can kind of match them onto EFT operators instead. So if we want to think about an EFT, these both correspond to dimension 6 operators. So usually you'll see in a dimension 6 Lagrangian, you would include an operator that looks like this. And then for S, and then this has to do with couplings between the Higgs and the gauge fields. Okay. So this one, as you should see in the T here, if you plug in your covariant derivative of Z, and you put in one of the vebs for the h, you can see that this thing should give you a correction to the z mass. Okay, so this thing we usually like to think of as the operator that parameterizes how badly custodial symmetry is breaking. So if you remember this fun parameter rho, which is predicted to be 1 at tree level in the standard model. This will start to be violated because how we calculate the z will no longer have the simple dependence. So T you should think of as the measurement of how badly custodial symmetry is violated. So this is something that again would indicate the presence of new physics. All right, so the reason why we don't consider U is because U is similar to these but dimension 8. So that means it's going to be suppressed by another 1 over lambda squared. So it's really hard to model build a way that would be a dominant contribution rather than one of these two things. So we consider U to be set to 0, assuming that would be a higher order effect. Okay. So now, if we put in these new radiative corrections, we have an updated W mass, which will look like what we would get from just the standard model parameters, but now we need to add in some contributions from these radiative corrections as well. Okay, and then times S minus 2. Okay. So the W mass and all these other standard model observables that I mentioned before will get new corrections from these radiative, these oblique parameters, and then we redo our fit, and then we find for which values S and T will also minimize this chi-squared fit, and then that kind of tells us again how we expect these new physics to be showing up. Okay.
So the U parameter does not show up for.
U parameter would show up. It would show up. Yeah, so it would be similar in coefficient here, but again, we would expect the value of U to be suppressed by, thank you, this 1 over lambda squared. So we're just saying that phenomenologically it doesn't really make sense for this to be as big of a contribution as the other two. Okay. All right, so here is our fits done with these S and T parameters. So we have S over here, T over here, and again, consistent with the standard model, we would expect these things to be 0. So this point here is what the standard model would predict. Yeah.
So what breaks the degeneracy between the S and T?
What do you mean?
Well, I mean, because you can just choose two different S and T to have the same W mass contribution.
Sure, but yeah, so this is just W, but it also shows up differently in all the other observables.
Yeah, but the W mass is the only beyond the model observables, and the S and T is only beyond the model.
But all of the other observables that I put up will get different contributions with S and T if they show up as well too. So all of these things, I erased it, but all of our standard model predictions will get adjusted by S and T, and that breaks the degeneracy between S and T. Yeah, good question. Okay. So just to kind of flash through again what these different fits are. These are the 2 sigma fits according to our chi-squared fit. And these different lines are, first the blue is just the PEG. The orange is considering just the other experiments that don't have to do with CDF, so LHC, LEP, and the tevatron, so that is confirming those to be fair. Then we consider 2 extra fits. In green, the CDF with double the error bars, and the orange is the CDF just as it was presented, so taking that to be the W mass. Okay, so before the PDG fit at these central values of S and T being very close to 0, 0. With the CDF-II measurement, it cranks these things way up to be almost 0.2 each. But if we instead take our updated world average, where we're really considering all of the data, then we have something like 0.12 for S and T is 0.2. So we see with this orange curve that it's actually consistent with having an S equal to 0 value. So in order for kind of simplistic interpretations of these things, we're really just going to focus on this T value being non-zero, and then see what kind of new physics models could contribute to Okay. So let's just get a quick order of magnitude estimate. Yeah.
How many sigma ways 0, 0 SNT from the CDF-II measurement? It just enough fit
That's a
you.
good question. Let's come back. Let's see. I need to rephrasing. I don't know. We have the numbers in our paper just from looking at this. I don't know if I could give you a more intelligent answer. Okay. So just to kind of give you a quick NDA analysis, that's redundant, a quick NDA interpretation of what these parameters should be. If you want to consider what happens to give these values at tree, thank you, and loop level, okay, we want t to be about 0.12. Again, looking at our operator over there, we would expect at tree level, we would have this times some new energy scale 1 over lambda squared. And if we want this to be about equal to 0.2, then this new energy scale would be on a TEV. Okay, just NDA. If we do loop, then we need to throw in our loop factor. And that basically just makes the whole situation worse by a factor of 10. So new physics is giving us contributions to these dimension 6 operators at the tree level. The new physics could show up at TeV. If it's entering through loop, there might even be new physics hiding as low as 100 GeV, which is really exciting from a collider physicist perspective. Okay, so we had a lot of great questions, so I might skip one of my models, but I'll go into the more fun model that could.
Sorry, maybe I should have asked it.
Please.
Kind of this analysis already assumes that the way to fix the discrepancies to add some deviation. Is it kind of obvious that because when we add some like quickly interacting like lightish particle which affect what fermion or something like that, then it's pretty plane is very correct. And that will be like characterized in this way, right? So
That's true. We are kind of making a model and an assumption that a radiative correction is kind of the right way to go in general. And I think that if you were to use, I think notably the Y oblique parameter, then that would account for something more like coming from light radiation, like a light dark photon model perhaps could account for this. So while you could do that, it will be inconsistent with the particular electroweak parameters that we have chosen.
I think I got confused by your diagram with V and V prime, thinking you were imagining there was another Z prime boson.
Yeah.
Was that the sort of underlying?
Sorry, so V and V prime were just supposed to be Z photon W.
Okay, you're not introducing some new thing, but you're looking.
No, we're saying that all the new physics.
You're just explaining the oblique parameters.
Yeah. But again, I would encourage you guys to check out the Y or W oblique parameters if that is something interesting. This is something I've been starting to think about too. This is kind of the picture of how the dark photon could potentially fit into this picture and account for this anomaly. Okay, so the model I want to give you is a tree level contribution. So I just erased it. Let's erase it again. We expect this dimension 6 operator to give us our T parameter. So one possible model that we can consider is a scalar triplet Higgs. So we'll call this phi, and that has the representation of a triplet in SU2 and neutral and hypercharge. So if we write out a Lagrangian that has a potential with this, then if we have our kinetic term and we have an interaction with 2 Higgs, right? And a mass stroke. Okay. If we have this new theory, what will happen is that this new parameter phi will get a Vevnitz neutral component. So now, if we have a non-zero contribution to the Vev, which will look something like this kappa B coupling here times the Higgs Web squared over its mass, right? We see, just like in the Higgs mechanism, that that would give us a mass for the W. Again, through the covariant derivative, if we plug in our Bev, we would see there would be a correction to just the W mass, because it's going to be in the scalar triplet and only getting a component in the neutral, or getting a Bev in the neutral component. So that gives us an adjustment to the W mass, right? So that's a little fast. But just to show you in the EFT picture what this would do is if we have our Higgs. This is how we can generate this dimension 6 operator at tree level. Okay? So just again from dimensional analysis. We see that the contribution to T should look like kappa squared from these two couplings over mt squared. We know that the definition of this actually has a v squared in the numerator. So to give us the right units, mt squared here. So this is the thing that we fit to be about equal to 0.2. Okay, so putting this model in, we find that actually there is interesting. Yes. Okay. There's interesting parameter space for the mass of this new thing. You can kind of mirror the TeV scale. So kind of as promised from our NDA, about at the TeV or a little bit lower, there is this non-zero parameter space indicated by this blue curve, where something new like this model could actually contribute to the W mass to be consistent with this anomaly. So this particular model is not, hugely motivated by anything, but this kind of thing shows that there could be new physics lurking very near the scale that we have access to with colliders that could be starting to show up in measurements of the standard model. Okay.
And so what are the other constraints on the mass of, are there any constraints on like this regional parameter space, this type of like triplet?
You mean like have people searched for this kind of thing before?
I mean, I imagine they've searched for it.
Yeah. I don't think we're able to go up to this energy scale.
Right.
Yeah, is the thing.
So like the bounds are just like way lower than this.
Yeah.
I mean, this is the bound. This is.
Well, but this, I mean, there's no experimental bound. Is this
Yeah.
point? Yeah.
What is a direct bound? Like,
So like
if it's
a
500,
the bound from
500,
this
yeah,
measurement.
direct
Oh,
production.
it's really
500.
Yeah, it's not at this energy scale.
It also depends on
Electric brush.
precisely how degenerate these things are, right?
Yeah, so I mean, if you're a big Susie person, which I don't imagine everyone in the audience is, this is the swino that you would get. So if you want to compare it to a good bound, like the swino bound for an equals to symmetric situation would be the right way to check. But yeah. So I don't want to. I think I'll be out of time if I consider my other model. So I'll just flash it real quick. Is we consider fermionic singlet-doublet model. And then just to kind of give you the idea, if you have a bunch of fermions that have both a singlet, like a Majorana, and then a direct representation, these kind of things can also contribute to T at loop level via a diagram that looks like this, where we have fermions running in the loop and Higgs is externally, and that gives you kind of the loop picture for this. And then you can see that there are masses even at the kind of hundreds of GeV region that we might be able to see. And then this NF is just how many copies of this do you throw in there. Not the most motivated thing to do, but again, just kind of a nice illustrative example that hundreds of GeV or TeV new physics are not fully constrained, and they could be
These
starting to show
masses,
up.
there should be some bound probably.
Oh, absolutely. Yeah, there's LHC bounds. This is why this is a dumb idea, because this stuff is all completely ruled out by the LHC. But throwing in more families
Not the whole thing.
cranks it up, and so we don't have to worry about it as much. So yeah, I just want to leave you with the picture again of this anomaly. Whether or not you believe in this specific measurement is something that I think we really need to hear from the collaboration on. But the fact that there are indications where we can have new physics showing up even as low as hundreds of GeV or TeV is really exciting. And for me as a collider theorist, I think it's super fun to think that there can be evidence of new physics that really encourage us to go into the next frontier of colliders and build machines that can really reach those tens of TeV regions and see what else we can find. So thank you so much.
So I'm gonna go on kind of, I think, what Glennis maybe was sort of alluding at, which is that there's this if we go back to like G-2 and there are all the contributions and you measure the R hadronic, which maybe is part of that correction. And if I said, well, I don't know what those people are doing, but these BMW people seem really, really good. And I were to like take their value and I went and I used that for this correction instead of using theirs. Do you know what that would do? Is that a sensible, am I just saying words that actually don't make any sense?
No, I think it's reasonable. If you want to consider, like, there's another very well measured parameter, and this is the hadronic contribution to these couplings, right? I think, unfortunately, what we found is that if you were to include things that were consistent with the G-2 anomaly into this, is that the whole thing gets worse. Like, the models that would correct for a positive T would be inconsistent for correcting for the parameters that would give you the anomalous value of G-2. So like the anomalies go in opposite directions.
Although that's not, I mean, that's an interesting point, but it's not obvious that that's the same thing as if I went, because if it's not coming from a T correction, but it were coming from, for instance, like some, hadronic correction that needs to be taken into account, then that would appear in a different way.
Yeah, that's true.
And so I'm just wondering if there's any way to.
What is true is that if you use the old values of this list of standard model parameters, making that, let's say, the BMW correction, or getting agreement with G-2 by changing the alpha, it comes here as what you call delta alpha Z, I think.
Yeah,
alpha hat Z, that's a parameter. Anyway, if you change that to agree with G-2 and the hadronic factor polarization, it does make the fit worse with the old values. And the question that I guess we're both really curious about is, if instead you use this value for the mass, what is it maybe not a worse fit?
Or maybe even worse.
Yes, that's right. It might be even worse, or it might not. I tried to estimate it using a paper that had a sort of linear fit, and it seemed like it would be actually worse. Which would be really interesting. But it would be worse in a different way than this.
Yeah.
Which may be, so it'd be interesting, since you guys are set up to do that, to try that as one of a variety of scenarios for.
Yeah, definitely.
Yeah, if you had you were saying like that Dave Curtin had a paper there.
Yeah, David Curtin and sorry, just gonna steal your thought right there. But David Curtin and collaborators had a really nice paper that's like assuming that the G-2 anomaly persists, then there's like a no-go theorem that says there has to be new physics found with a muon collider at like a 3 TeV scale or something. So yeah, Neil and I were.
I mean, okay, like no-go theorem with like some assumptions they make, which is not really a no-go theorem, but like they have some assumptions.
Yeah, no, but I was just thinking that kind of like what Glenn is saying here is we need to do a sort of more a different global fit where you'd be like, if you took G-2 and you said, here are my possible solutions to it, and with standard model, and I said, here is this, my solution is standard model, only standard model, not beyond standard model, that there's trying to solve either one of them, by assuming some, correction to something that's hard to calculate.
Right.
It could be. If that would lead to it being like that the overall fit just stayed bad no matter what you did, then you have some sort of like no-lose theorem that like there's got to be something somewhere, right?
So you're saying like, what if we take like the worst interpretations of all these different things and try to mash them together, like?
Yeah, or that if it were like if I don't know how to think about these formulae in terms of the lattice calculations, but if you do say like, well, we just messed, extracting them from data with some problem, and we should use lattice or whatever, but you just allow yourself to like float the things where you might say there's some calculation uncertainties, maybe something hadronic, but you did the fit simultaneously.
Sure, yeah. So that, I think that was an interesting thing that we were thinking about doing a follow-up, is kind of like machine learning and like do this kind of thing where it's like, okay, we try to float like how many other things could go wrong, what other measurements are maybe inconsistent, what other error bars could be bigger, and like kind of float all of these things in a higher dimensional fit, then maybe you can figure out, okay, the fit would be consistent if this parameter had this central value for this error bar or something like that. Then that could give you, like you say, like a kind of no-lose idea of where the standard model is really breaking down and what thing needs to be measured better. But these are all nebulous ideas that haven't been done yet, of course.
Well, one of the things that I think itself would be very interesting is to say, well, supposing the G-2 tells us the line vector polarization contribution, and the W mass is this, for example.
Yeah,
what physics you'll get a very different conclusion for what your ST and U are. And just to know what that is, it seems like you might even sort of expand the matrix. Here you've
that's really important, right? If we're gonna build future experiments based off of anomalies, they should be
just
mindful
theory
of
thinking
anomalies.
about what
Yeah.
it could be.
Absolutely.
Okay, any more questions for Cari? If not, let's thank our speaker again.
I looked up your paper, and I think you just miswrote it wasn't sigma head that you were putting in as a